Graph500. I'm actually pleased to see the room packed here. This is a new benchmark that has been a community effort to complement the top 500 list for large-scale data analysis problems, the big data type problem space. Rich Murphy and the organizers have put together a very broad steering committee coming from multiple disciplines, coming from around the world, and you can see a short list up on the middle of this slide. And the idea is really to come up with the key kernels or problems that can drive the architectures to solve these new and emerging problems coming from graph analytics, big data analysis, and so on. At the start, and as Rich said, this is a work in progress, so that we imagine over the next few years, the next few lists, we gain more understanding in the space, we improve the benchmarks and kernels that we have, we learn how to rank and compare these systems, and we keep improving this benchmark till maybe 5 years out we have a very stable benchmark that will be useful for the community, both to drive architecture, to do procurements, and to really look at the value of these big data problems in the high-performance computing space. Early on, there was a thought that among the steering committee that we would have 3 kernels, one in search, and that's essentially what we have right now on the Graph500 list, looking at breadth first search. The second one we'll talk more about today on optimization, and then the third would be more of an edge-oriented type of kernel. And just to give you a little bit of history, this is a benchmark really at its infancy. It was first announced just a year and a half ago at ISC 10 in Germany, and the first list was 1 year ago at Supercomputing, where we had 9 entries, heroic efforts to implement this benchmark in time for supercomputing last year. The second list came out 6 months ago at ISC in Germany and had 29 machines on that list, and today we're really pleased to have 50 entries on the list. So this is really growing in importance, as we see from the attendance here and also from the amount of industry support, those of you who are developing systems and libraries, and the whole community has really taken this to heart. There's also a lot of open challenges on how to compare these systems, how to spec out the next benchmarks, how to validate them, and it's a learning experience. And so I hope today you'll see an argument with Mark and Andrew up here, who are going to put on the gloves and battle it out with some of the arguments or discussions in the steering committee. The Graph500 really aims to capture a number of new and emerging business areas coming from cybersecurity, medical informatics, social networks, data enrichment, and symbolic networks, to name a few. So for instance, in cybersecurity, we're trying to sift through billions of log entries. In medical informatics, we know that health and medical records are a huge problem for clinics and medical institutions to try to come up with personalized medicine. In social networks, we want to gain understanding from social media, from Facebook, from Twitter, with these growing data sets of enormous proportions. In symbolic networks, there is a lot of interest in trying to simulate the human brain, simulating billions of neurons working together. These are the types of problems that are often very irregular in nature, often very hard to parallelize, often have concurrency, but hard to pull out the locality with the concurrent operations. And so these drive memory system designs, they drive new architectural designs, and we're hoping that this benchmark will be a surrogate for the application space in this emerging area. We have a webpage, graph500.org, and Jeremiah Wilcock, who's in the audience, has told me he's going to flip the switch right.
He already did.
He flipped the switch, so if you go live and crack open your laptops, you'll see the next list that we're announcing today live at graph500.org. You can find out more about the specifications, more about the previous lists, and so on from this site. So now, drum roll, the rankings. So what I'm going to do is tell you first a little bit about the list, and then we'll go through the top 10 machines. But you can go on live and look at the site to get information on the top 50. This list has been grown by a great amount in the last year, so there are 9 entries on the order of 30. Now we have about we have 50 entries to announce at this third Graph500. And the entries come from around the world, so a majority come from the US, about 74%, but we have a number of machines in Japan, 2 in Russia, 2 in Germany, 2 in Switzerland, 1 in China, and 1 in the UK. So this is really a international effort, and I see many friends in the audience from around the world. We're very pleased by the participation. So starting with number 10 and working backwards, I'll ask those who have received these to come up and grab their certificates. Maybe if people want to take a picture, I'll have Mark and Andrew hand out the 10 certificates in reverse order. So number 10 is Sandia's ultraviolet system, and on the award here, it achieves 17 billion edge traversals per second, a measure of the performance rate on this graph-theoretic benchmark. And the problem scale here is 29. What that means is the graph was created with 2 to the power 29 vertices, or 500 million vertices, for this benchmark of starting with one vertex and then traversing through or visiting all the vertices in the graph by traversing edges in that graph. So if anyone's here from Sandia to collect the ultraviolet certificate. Number 9 is from Lawrence Berkeley National Lab, the Franklin system, with 20 billion edges traversed per second on a problem of a very large scale, scale 36, which is 64 billion vertices. Anyone from LBL?
That's wrong with me the last time, right?
Okay. So Rich Murphy isn't here, and that means I can blame him for any mistakes. So we'll double check that. You still can get. Oh, number 8, also from LBL on the Hopper system, 25 gigateps on scale, giga-eps if you will, teps, sorry, billion traversed edges per second on scale 37. That's a phenomenal size problem, 128 billion vertices. Don't tell me they're all wrong. I'm just looking at the data. It says SC11. So I think what he kept the entries that were submitted the last time and then incorporated new entries as well.
No, that's not.
No? Okay, so we'll hunt it down afterwards.
Well, I mean, this is wrong every time.
So number 7 is IBM Blue Gene Q from TJ Watson with 56.5 billion edges traversed per second, scale 30. Fabrizio? Thank you. That's right.
We won't argue what's happening.
Yeah, maybe it's a rounding error. So Intel's Endeavor, and this is a very interesting system, number 6 with 57.6 billion edges per second on scale 32. Number 5, Argonne National Labs Intrepid system with 78.9 gigateps on scale 35. Number 4 from Germany, the Jülich system, Jugene with 92.9 gigateps on scale 37. So number 3 from Japan, Tokyo Institute of Technology's Tsumabe system with 100 gigateps on scale 36. Congratulations. Number 2 from Russia, Moscow State University and T-Platforms, the Lomonosov system and Anton Kirsch with 103 billion taps on scale 37. And number one, he knows already. It's it's on the web. It's on. T.J. Watson's Blue Gene Q Prototype 2 with an astounding 254 billion taps on a scale of 32, which is 4 billion vertices. Professor?
The full name is important. T.J. Watson, NNSA, SC,
Find the name and to have the actual name.
That's why I say it.
So the also is for large vehicle and for the OEM, you also make your also for the same thing. Right?
Yeah, there's multiple.
Yes,
There's multiple certificates here for the team. So again, it's the IBM Research T.J. Watson's NNSA SE Blue Gene Q Prototype 2.
You are SC.
So congratulations to these top 10. So the list has 50 entries. We have certificates for all of the other entries. So if you submitted, we have your certificate. After the BoF, come around to the outside, and myself, and I've asked Jason Reedy, who's sitting over here, and a few others to help sift through those to give you your certificate. And our program in the BoF continues, where we have a few announcements and discussion, and some of the leaders will want to talk.
Yeah, before we do that, I really have to explain this complex name of the winner. It's Blue Gene Q, which is still at IBM, but which will be deployed at Lawrence Livermore. It will be deployed at Argonne, and it was a joint effort of IBM and the two labs which are working with IBM on Blue Gene Q. Hence this complex name. But congratulations to all the winners.
So we've debated at some of the prior BoFs and among the steering committee of the next kernel that will be included in the Graph500 benchmark suite. And there is convergence on doing single source source paths. And shortly there will be a formal spec that will be released after full discussion by the steering committee. And I should note that the next Graph500 list, the fourth release, will be at ISC 12 I believe it's May or June 2012 in Germany, and it will include kernels 1 and 2, so both the search problem and the source path. This opens up a lot of discussion on how to compare the benchmark, or whether or not to have a single number for this rank list, or to be able to sort through different types of numbers on the different kernels. So there's a lot TBD, and that's what we'll hear from shortly on some of the ways to rank the Graph500. Now this proposal on single source source path, I have a couple slides, and these will be made available on graph500.org. There are some issues with the graph generation and breadth first search that have been raised. For instance, isolated vertices and permuting vertex numbers is often expensive. And what we're going to try to do is perhaps clean up the generator a little bit. The problem kernel for single source source path will be to compute non-negative weighted single source source path. So given an undirected graph, similar to what we have with the breadth first search kernel now, we want to compute a weighted shortest path tree from a source vertex to all other vertices in the graph. And undirected here is equivalent to bidirected. So if we have an edge from U to V between two vertices, we think of that as equivalent to having an edge from U to V and also from V to U with the same weight. And so the proposal is to select edge weights at random on the current graph, perhaps from some small set like the integers from 1 to 32, and to run single source shortest path on this graph. So there's a lot of